So this is halfway through, but the decay is now collapsing that phasor down. That's the idea. Let's look at some different values for S. What could S actually be? So let's suppose, to begin with, that V of t is equal to V sub m e to the st. Suppose now that we let s equal 0. What happens to this variable v of t? V of t is now v sub m e to the 0t, which is equal to v sub m. But that's not a function of time anymore, is it? This is now just a constant, or some DC value. And when did that DC value occur? Well, that occurred when s was equal to 0. Therefore, signals with s equal to 0, we can think of those as corresponding to constant or DC waveforms or signals. What if we go back to something that we've tried before, or that you were working with in ECE 220? If we now replaced S with this phasor, j omega, then what happens? Then we get this signal, V of t, that's now V sub m e to the, replace S with j omega t. And that you should be okay with. That was this complex spinning phasor from 220. And if you wanted to go back into reality, we could simply remember Euler. And with Euler, e to the jx expands into, do you remember? Cosine of x plus j sine of x. Meaning if we want little v of t to be real, we could just extract the real piece or the real component of the e to the j omega t expression. Meaning if we now want to a real signal, we can make that by simply saying extract the real part of this v sub m e to the j omega sub t complex spinning phasor. This is now the real part of v sub m cosine omega t plus j v sub m sine of omega t. And this function, real, of the curly braces just says pull out the real component of that complex expression, and little v sub t now becomes a real sinusoid. And when did we get that? For what choice of S? We assumed S was just j omega. So now we've seen what happens when we let S be 0. We get a DC signal. We have 0 frequency. That seems to make sense. We get a constant waveform. We now inject, or we allow our frequency to be purely imaginary, and now that gives us, if we pull out the real part of that, this cosine, or now we can get sinusoids out of this complex frequency variable S. What if we go all the way and we say, what if S is equal to minus sigma plus j omega? Then this little v of t becomes the real part of v sub m e to the minus sigma plus j omega t. But that's just the real part. If we split that exponent, we have v sub m e to the minus sigma t e to the j omega t. The only thing that's complex inside the curly braces right now is the spinning phasor, e to the j omega t. The decay is all real. V sub m is a real number. So we now have v sub m e to the minus sigma t, the real part of e to the j omega t. And we just learned how we could treat that through that function real. So that now we have v sub m e to the minus sigma t cosine omega t. We get then for our signal, little v of t, an exponentially damped sinusoid when S is equal to minus sigma plus j omega. And now we have maybe a little bit better feel about what this S could do for us. We can now create different types of signals in terms of this complex frequency variable S. And we want to be able to analyze circuits when they might be excited by these different kinds of signals: constants, sinusoids, exponentially damped sinusoids. We might like to excite our circuit with those signals. Let's do some circuit analysis. Uh-oh. Wow. Let's start with a fairly basic circuit. Let's say here is a yet to be determined or specified voltage source, which is going to be applied to a resistor and a capacitor, and I'm going to measure, or my output for that particular circuit, let me just say, is the capacitor's voltage. And now you're in the interview and he says, can you analyze this circuit? And you all should just, in your mind, jump up and down and go, yes, 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 I know how to do this, I know how to do this. I'll just stay calm and act. How do we analyze this? What do we focus on if we want to write? And now maybe he says, oh, can you do it via differential equation? Can you write the differential equation that governs the dynamic behavior of this circuit? Can you express this circuit, or can you write some equations that involve the source, V of t, and maybe a key variable in the circuit? What's our strategy for picking key variables in a circuit? Do you remember when we have capacitors and inductors, what do we want to probably key in on? I have an inductor, what do I probably focus on based on Eli? What's differentiated in my current voltage relationship of an inductor? The current. So we want to work with currents and inductors, and if we do the same kind of thought process, ICE tells us what variable is differentiated for capacitors, the voltage. So we want to focus on the voltage of our capacitor, meaning we might want to write these equations in terms of the capacitor voltage. That's our strategy. So if that's what we want to do, what's KVL give to us? If I start down here and I march around that mesh, I only have a single mesh. I'm going into the negative terminal of my voltage source, so I'm going a minus V of t plus R. I want this voltage drop here across that resistor, but that's got the same current as that capacitor has flowing through it, which is flowing through the source, so we only have a series circuit, plus, the capacitor voltage, let's just write that down, plus V sub C is equal to 0. And now we have three different variables. What good is that? Well, the V is our source. That's going to be told or given to us. We can leave that as is, V of t. But now we want to focus on the capacitor voltage, meaning we probably want to rewrite the capacitor current in terms of the capacitor voltage. And that's where ICE comes in. ICE tells us the governing current voltage relationship of a capacitor. That says that I sub C of t is equal to C dV sub C dt. And if we put that into our equation, we have minus V of t plus R, and now replace I sub C with this C dV dt, C V sub C prime of t plus V sub C of t is equal to 0. And now we have a first order differential equation in terms of the capacitor voltage. And that's what we would have expected because we had one energy storage element, one capacitor. So this is not unexpected. This should be an expected result. Now we could rewrite that if we wanted our coefficient that scales V sub C prime to be unity, we can multiply both all terms or divide all terms by RC. So we can now rewrite this, and suppose I put the V of t on the right-hand side, I can now say V sub C prime plus 1 over RC V sub C of t is equal to 1 over RC V of t. And that may be more close to what you're used to seeing. We now have a differential equation that explains or tells us how the capacitor voltage is influenced as a function of time, given a particular source input, V of t. Now we can apply our Laplace transform techniques. We can Laplace transform this equation. And the Laplace transform is a linear operation, and we can then Laplace transform each of the three terms. Meaning this is a time domain equation. What we want to get comfortable with now is working in the frequency domain, because then the differential equations becomes algebra in S. Let's now take this into the frequency domain. by Laplace transforming the differential equation. So that now I can Laplace transform the derivative of the capacitor voltage. The 1 over RC is a constant. I can pull that out, and I only really need to worry about Laplace transforming the capacitor voltage, and the same on the right-hand side. And that's doable because the Laplace transform is a linear operation. I can break that down into 3 different Laplace transforms if I want to. What does this first piece produce when I Laplace transform a derivative? That was probably part of your homework, or at least we derived that in an earlier lecture. What happens with the derivative when you Laplace transform it? Where does S go? How does S appear in the formula? You're multiplying. So now you have a multiplication by S. You now have S, Laplace transform of little v sub c becomes capital V sub c of S. Is that the only thing I have to worry about? Then in general, I have to worry about the initial condition, don't I? So this is now minus V sub c of 0 minus. And that's coming to us from that piece. Then if we Laplace transform this second piece, we don't know yet what little v sub c of t is, and so we simply say, oh, we have to have its Laplace transform capital V sub c of s. That's as easy as that step is. And finally, for the right-hand side, we now have 1 over RC, and just like we did with little v sub c, we simply say, okay, little v of t, when we Laplace transform it, will give us this capital V of s. What we want to do now is try to solve for capital V sub c of s, because that will give us then some expression for s's that we can inverse Laplace transform to obtain little v sub c of t, the capacitor voltage in the time domain. Let's then combine the terms involving capital V sub c of s. Meaning we have an s V sub c of s, and we have a plus 1 over RC V sub c of s. And let me push everything else on the other side. I have the source term, 1 over RC V of s, plus the initial condition. Just algebra. And now I can factor out capital V sub c of s to make it by itself, which allows me now to write s plus 1 over RC V sub c of s equaling 1 over RC V of s plus V sub c of 0 minus. Do you remember what we called that particular piece that is weighting or scaling or multiplying our variable of interest in the frequency domain? Pardon? And what is it? It's a polynomial, isn't it? So that's our characteristic polynomial. Let's divide all sides by that characteristic polynomial, and now we can isolate the variable that we want, which is V sub c of s. V sub c of s now becomes 1 over RC. That's just some number once we are given R and C. Once we go to Josie and request a resistor and a capacitor, that's just going to be a number. Then we have S plus 1 over RC, S plus that same number, and that's scaled by our forcing function, V of S. And we have a second term that involves our initial condition. Again, scaled by dividing by that characteristic polynomial. This square bracketed piece, we will start to call that the transfer function. That transfers the signal, the input signal, our source, capital V, to an output signal, V sub C. And if we had 0 initial conditions, we would just need to worry about that transfer function and how that maps. And so you could think of that transfer function as, depending on what it is, but it's one way of thinking of it is it's just a filter. It's a glorified filter. You're now filtering an input and creating a new signal for the output. That transfer function, just to get something concrete, you could say, oh, that's a filter. In fact, it might be an automobile. It might be an airplane. You can model all sorts of things with transfer functions. It might be an optical system. You'll now have a transfer function, and once you get comfortable modeling with transfer functions, you can work in all sorts of domains. Last time, I believe, we identified these different pieces. This, we said, was the piece of our response that's being forced by the input, capital V of S. And the second term is due to our initial condition. Now we have a frequency domain expression, and maybe we don't want to be in the frequency domain. That put us where? Up here in the frequency domain, and we liked playing up here because it was just algebra. But now we need to go back into the time domain to obtain little v sub c of t. Maybe your interviewer said, I need to see this in the time domain. I can understand now you understand transfer functions, characteristic polynomial, poles and zeros, and we'll soon get to Bode plots, and you could draw a frequency response of this low-pass filter, and the interviewer would be sufficiently impressed, and he would say, here's your contract, right? And you would say, let me think about that. Right on cue. Let's take this now into the time domain. Well, let's clean this up a little bit by making some assumptions. Let's suppose that somebody says, suppose that the capacitor initially was charged up to where it had a voltage of 2 volts. And suppose that they say, what if we apply to that as a source, what if we just turn the switch on with an amplitude of 1 at time 0, or apply a unit step for the forcing function? What would you do then if you now need to find capital V of S? That's one of the first pieces that you have to produce in order to work the rest of this problem. What's the Laplace transform of a unit step? And on the exam, you can simply write this down. You don't have to rederive anything. You just know it. You've already figured this out up to now, or up to the exam. You know what the Laplace transform of a unit step is. That's in table 12.1. And you'll have that table for the exam. You now just pull this up, and what is it? 1 over S. now we can rewrite the expression for our capacitor voltage in the frequency domain. That now becomes this capital V sub C of S is now 1 over RC, S plus 1 over RC times S. And we had our initial condition term. And we said the initial condition was 2, and that was also over this 1 over RC. And if you went to the stockroom window and ordered up your meal, which consists of an R and a C, you can make that whatever you want. To put the pole, the value of S that causes this characteristic polynomial to vanish, you can now place that wherever you want. If you wanted a 10 radian per second bandwidth, then you would want to pick 1 over RC to be 10. If you wanted your low-pass filter to have a bandwidth of 100 hertz, then you would pick 1 over RC to be 2 pi times 100. This is an omega quantity. So it's now 200 pi. And you would set 1 over RC equal to 200 pi. And Josie goes, we're kind of low on capacitors. Here's a 1 microfarad capacitor. Then you're forced to go back and design for your resistor to figure out what bandwidth you need for the filter that you're designing. Let's just keep it, though, in terms of 1 over RC for now. Is it clear, though, what we're doing? If we now want to solve this or put this into the time domain, what was our strategy? I'm really helping, I thought. If we now create a partial fraction expansion based on this blue line that's still on the screen, how would we parameterize a partial fraction expansion? And I might say on a test, give me the structure of your time domain answer. And so I'm really looking for, can you find a partial fraction expansion and immediately jump to the time domain equation? The last term, that 2 over S plus 1 over C, is done. That's fine. Once somebody tells us R and C, we can immediately give an exact expression in the time domain. Is this first term finished? How do we rewrite that as a partial fraction expansion? Let me do it this way. Is that okay? We have two terms. They're all depending on what the denominator, how it factors. And it's already factored for us. We have one factor that's simply S. That's a pole at the origin. And that was due to the stepped input, wasn't it? And we have another factor, S plus 1 over RC. What's the time domain answer going to look like? Now you go back to table 12.1, you look in the right-hand column and you go, okay, do I have any 1 over S terms in that, or expressions in that right-hand column? And if I do, then I just read across to what it corresponds to in the time domain and I write down my answer. That's now A times whatever that was. And what's 1 over S in the time domain? The unit step. So I now know that this is A U of t in the time domain. And if I can find A, I've got that piece. What's my second or middle term going to produce as far as an expression? I think I heard it. If 1 over RC became 3 as a number, I now have B over S plus 3. What would that look like in the time domain? B times what? e to the minus 3t, right? It's just an exponential decay. So that now I have b e to the minus 1 over RC t. Now can you write down the third term? That's exactly the same structure as the middle term, isn't it? So this is now 2 e to the minus 1 over RC t. And we need to remember that all of those are only on for non-negative values of time. This is starting at time t equals 0, this structure. If you were to go back and find these coefficients, you would actually see that a becomes 1 and b becomes minus 1 if you actually solve for those using partial fraction expansion, which now says that we have 1 minus e to the minus 1 over RCT plus 2 e to the minus 1 over RCT. Or you might see that written, and can I combine those last two pieces? They're all the same except for the coefficients, and I now have 1 plus e to the minus 1 over RCT, and somebody might write that this way. And that's equivalent to 1 plus e to the minus 1 over RCT, t greater than or equal to 0. Can you see the time domain response that results from this? What did we do? We applied a voltage of a step at time 0. If your interviewer said, draw me a picture of the voltage on the capacitor as a function of time, when you applied a step input, where are you at time t equals 0? What value? We replace t with 0, and we now have 1 plus e to the 0. We have 1 plus 1. We're at 2, aren't we? After a long period of time, what's going to happen? That initial condition is going to decay away, and we will just be what? At 1, which is our step input. That's what we applied, and we keep applying it for all time. Meaning we are going towards that 1 value, and we're just exponentially decaying towards that value. Whew. That's supposed to be a smooth curve, exponential. Now, for all practical purposes, how long do we have to wait before we get to 1? How long do we have to wait before we get to our final value? We're approaching 1, aren't we? If we apply a step to this low-pass filter, and the step has a magnitude of 1, then how long do we have to wait? We have to wait until this guy becomes negligible, right? We want e to the minus 1 over RC times t to be small. And what do we mean by that? Well, typically, we might say e to the minus 5 is small. And that's 5 time constants is what that's referred to. So now we're less than 1% of that e to the minus something t. If we just had that term, that's 1. Now we're down to 0.01 in 5 time constants associated with that factor. Which says that if we set 1 over RC to this, let's say t weight, we want that to be 5, don't we? And t weight, or how long we're waiting before it starts decaying, is 5 times RC, and we will eventually be calling this our time constant. We had a first order system. It has a single time constant, and so if we wait 5 time constants, if we just have one time constant to worry about, if we have a lot of time constants, we pick the slowest one, and we wait 5 of those slow ones. But if RC is now 2, let's say RC ended up being 2 seconds as a time constant, then we would be waiting 10 seconds to get to 1. And that's pretty slow for an electrical system to have a time constant of 2. Typically, we're in the milliseconds, aren't we? So this exponential decay, or even faster. After 5 time constants, we are close to our steady state value, which in this case was a constant. What if we looked at a different possible driving source? What if we say, you know what, I kind of know what will happen to that initial condition. Let me just neglect it. So let me just set that equal to 0. Let's say that the capacitor is not charged up when we throw the switch. And suppose that we turn this on by applying a sinusoid at 0. And I'm not going to specify the frequency. I want to keep that variable so that you can kind of see where that variable frequency comes into play. But now omega could be 10 radians per second. It might be 1,000 radians per second. If I gave you an input and I said, oh, I need to excite this circuit with a 60 hertz waveform, what's omega? 377, thank you. 2 pi times 60, right? So if you don't remember 377, you can go 2 pi. Oh, that's roughly 6. So 6 times 60, 360. You're in the ballpark, right? 360, 377, that's pretty close, give or take. That's pretty good, okay? 377. But we could pick that omega to be whatever we want. Whatever it is, what is our Laplace transform of that little v of t? Now you just go to your table, right? Table 12.1, and you find, in the time domain column, you find this cosine. What's the denominator look like of a sine or a cosine with frequency omega? And it's not damped, is it? This one just sits there and shakes. It just keeps shaking, doesn't it? This is 220. I don't think Dr. Marsland did this, but this is what was happening. In 220, all you did was shake. Once you start shaking, you just keep shaking. In 320, we're going to damp those out. We're going to allow those to be exponentially damped so you can be done. We're going to have mixing of transients and sinusoidal behavior together. So we can now be finished instead of just sitting there like this. But now what are we doing? Please answer. We're just shaking, aren't we? With a frequency of omega. What's the denominator when we shake at omega? S squared plus omega squared. And the only thing that changes between a sine and a cosine is the numerator. What's the numerator look like when we have a cosine? That has an S, doesn't it? So there is our Laplace of the driving signal, capital V of S. We don't have to redo any of the circuit analysis. We've already got our transfer function from the original analysis, so that we can now write immediately the Laplace transform of our capacitor voltage. That's our transfer function, which we derive to be 1 over RC over S plus 1 over RC times the source, its Laplace transform, capital V of S, which is AS over S squared plus omega squared. And if I simply ask you to find the Laplace transform of the capacitor voltage, you would be done. This would be it. What if I said, I want to see the time domain answer? Now you have to do the inverse Laplace, the partial fraction expansion. What's the partial fraction expansion of V sub C of S look like? How many terms are you going to have? And what are you looking at? To do the partial fraction expansion, what do you focus on? The denominator. You look at that denominator expression and you try to factor it. You factor it into real factors and potentially quadratic factors that correspond to complex poles or complex roots. How many factors in this partial fraction expansion are we going to have? Kind of a trick question, actually, because now when we shake this as a sinusoid, we could see cosine and sine. We don't yet know, because it might be what? It might have some phase shift relative to the source that we're exciting it with. But if we hit this system with omega, that system is going to shake with omega. It's not going to shake with omega sub 2 or omega sub 3. It's going to shake at the same frequency that we're exciting it with. It's a linear system. We're not introducing any new frequencies. We hit it with omega, it's going to produce omega. And what else? What's that S plus 1 over RC producing in the time domain? I'm going to have to jump up on the table. It's going to get this an exponential damping, isn't it? An exponential decay towards our sinusoidal steady state. Because we're not going to quit, are we? If we're shaking it, we just keep shaking. That's what that's what V of t said. Once we start at time 0, we don't stop shaking. So that system will just start getting into a sinusoidal steady state behavior at a frequency of omega. And you might see a cosine and a sine at that same frequency. If that's the case, then it's going to be a little bit more than 2 terms. It'll be 3 terms, because now we have 2 terms associated with the sinusoids, a cosine and a sine. And we have to figure out how much of each we have. But what are my pieces now? I have an A1, S plus 1 over RC. Is it clear where that's coming from? That's the very first factor in the denominator. And now I have the pieces due to my sinusoidal excitation. Even though I applied a cosine, it may start looking like a combination of a sine and a cosine. Or you could say a cosine with a phase shift. That's the same thing. They're equivalent. So you could say, oh, I just have a magnitude and a phase associated with this cosine waveform. If I now put this as a B1 and I say this middle term I want to be associated with my cosine, what do I put in the numerator in addition to B sub 1? I need to put an S. Do I put anything in the numerator here? If I want it to have the same structural form as the pairs, the transform pairs in table 12.1, what do I want in the numerator? Omega. And then, once you have that omega, we can immediately put this into the time domain expression. If I wanted to solve for a sub 1, well, I don't know that I want to. We'll do that in a minute. Okay? But what is v sub c of t, little v sub c of t? If this is my structure in the frequency domain, what's my structure in the time domain? And I can allow you to just keep it in terms of A1, B1, C1, 1 over RC, and omega. Is that okay? That's just an exponential decay, and it depends on what I've picked for R and C. The middle piece. That immediately just falls out, doesn't it? That's exactly the row, one of the rows in my table. S over S squared plus omega squared. And the other row produces and this is true once we hit 0. What you can observe from this answer is those are special frequencies, aren't they? That's exactly what I hit it with to begin with. That was the frequency of little v of t. This was the input's frequency. And what do we know about this piece? What was my circuit? I said no initial condition and apply a cosine at 0 and just keep hitting it. What's going to happen to my result? Well, you just derived this. Now you have 3 pieces in your answer for your capacitor voltage. But how long are we going to have to wait before that green bracketed expression is gone? 5 time constants, right? Where a time constant in this RC circuit is just RC. So we wait 5 time constants, and now we're just in the sinusoidal steady state, practically. I mean, theoretically, we're waiting forever, right? That e to the minus never is gone completely. But practically, when we get within 1%, that's good enough. That's 5 time constants. So this is simply a transient term. And it depends on what you bought at the stockroom window, right? It depends on R and C. I always sort of play with Josie. I go up and order a cheeseburger at that window. She doesn't like that. But I can't write that on my little form. I want to check out a cheeseburger. She goes, you have to return it. You won't want it if I return it. All right, any questions on this? Is this helping with Laplace transforms? Do you now see what's going on? Now you can excite these circuits. Now your circuits can be much more involved. As long as you can derive the equation that describes the behavior of that circuit, now you just do what we've been doing. You multiply that transfer function by the input. It's Laplace transform, and you can find the output. Let's now focus a little bit more on this last step, which is the partial fraction expansion. That's the inverse Laplace transform stuff. I'm hoping now that you have a better feel for what S is going to do for you, or what it helps you do. Now, the one thing that you need to keep track of, or to be aware of, or always be cognizant of, is this partial fraction expansion. It's true for all values of S. And we can use that to our advantage to solve for some of these residues or partial fraction expansion coefficients. So this partial fraction expansion is true for all values of the complex frequency variable S. And last time, I think I stated that there's only two cases to really worry about. If we factored our denominator polynomial, if we factored the characteristic polynomial, and every one of those factors is distinct, so we might have a -2, a -3, a -4 plus and minus j7. That's now 4 distinct roots, and we would be in case number 1. If we had factored that polynomial and we have an s to the -2, an s equal to -2, an s equal to -2, an s equal to -2, we have a repeated factor or repeated roots, and we would be in case number 2. And we would have to apply slightly different procedures for finding the partial fraction expansion. But we only have to worry about these two cases. If we have distinct roots, it's pretty straightforward. So let's look at that case first. Case 1. Is when we have distinct roots in our denominator polynomial. Suppose that, just for illustration, I have some numerator polynomial, I'll call it numerator sub 1, and I now have s plus p1, s plus p sub 2, and s plus p sub 3. And I hope by my notation it's clear that p1, p2, and p3 are not the same. They're distinct. And let me go ahead, and what else do we need to know? In order to do the partial fraction expansion, what do we need the degree of n sub 1 to be relative to this expression? Before we start doing the partial fraction expansion, we may have to do some long division. When would we have to perform long division? When n1 is higher or the same degree as the denominator. So if n1 was of degree 3 or bigger, we would have to divide it out. So in this case, we want the degree of n1 to be strictly less than what? 3. Let's just make that assumption. So now n1 is a quadratic, a linear, or maybe it's just a constant as an expression. Any of those are fine. What's the partial fraction expansion look like for capital F of S if we have distinct poles or distinct roots of our denominator? I'm mixing it up on you. But these are different coefficients, aren't they, or residues? And now if we knew A1, A2, and A3, we could find the time domain expression. Now remember, P1, P2, and P3 could be complex. But in this partial fraction expansion, we need to solve for, or we need to figure out or find A sub 1, A sub 2, and A sub 3. Do you remember the method to do that? A sub I is equal to what? I multiply every term by the denominator expression associated with my coefficient of interest. In this case, if I wanted A sub 1, I would multiply everything by S plus P sub 1. And in particular, I'm multiplying the left-hand side by that. That's going to cancel one of those, that same factor in the denominator of f of s. And then I evaluate it where? Where that factor vanishes, which is the value of s equal to minus p sub I. If we looked at this in terms of an example of just this third order that I've put together, we now have s plus p1 times f of s. And we want to evaluate that at s equal to minus p1. But when I do that multiplication, the s plus p1 in the numerator cancels the s plus p1 factor in the denominator of capital F of s, and I'm simply left with n1 of s over s plus p sub 2, s plus p sub 3, evaluated at s equal to minus p1. That's what I end up with on the left. Now what do I end up with on the right? If I multiply all of these terms by s plus p1, the first term, I immediately isolate capital A sub 1, right? Because I've just canceled the s plus p1 factor. And the other terms, I'm left with that s plus p1 upstairs. I now have on the right-hand side a1 plus a sub 2 s plus p1 s plus p sub 2, but I'm evaluating that at s equal to minus p1 plus a sub 3 s plus p1 s plus p sub 3. And do you see what's going to happen to these last two terms? When I evaluate those at a value of s equal to minus p1, I'm forcing that numerator to 0, aren't I? So I don't have to worry about that, and that allows me to isolate on the one coefficient that I was wanting, which was a sub 1. Meaning I can now find a sub 1 is equal to n sub 1 of s, the left-hand side, s plus p sub 2, s plus p sub 3, all evaluated at s equal to minus p1. All right, let's get specific. Let's put some real numbers on this. Let's do an example. And suppose that somebody says, okay, capital F of s is 2s squared plus s plus 4 all over s plus 1, s plus 2 squared plus 3 squared. Do I have distinct roots in my denominator polynomial? And I'm going to write it like this a lot in this factored form. And I want this to just jump right out at you. And if it doesn't, you need to go home and convince yourself where the two roots of s plus 2 quantity squared plus 3 squared live, or where they belong. Do you see that one of these poles or factors is right there, right? That's the easy one. But now if I replaced s in that bracketed, square bracketed factor in the denominator, if I substituted in minus 2 plus j3, do you see that that would vanish? And if you don't, go home and do this. And if you plugged in minus 2 minus j3, that's going to vanish also. So this is now going to be one of my roots, or I'm sorry, one of my factors with a root at minus 2 plus j3. That's in the third quadrant in the complex S-plane. And then I have a root or a factor s plus 2 plus J3. That's the conjugate of the previous one, and it's going to be in the, where did I say? Did I say the second quadrant on the first one? Where are these poles? Or where would I, so this, whoops. The pole is where that factor vanishes. That's at -1, isn't it? What about this one? If I replaced S with -2 plus J3, does that vanish? That's now in the second quadrant, isn't it? What about this one? What value does S need to take on for that factor to go to 0? -2 minus J3. So that's the twin of that middle factor, isn't it? It's its conjugate. They're across the horizontal line from each other, the same distance away from the horizontal axis. What if I now want to solve for a sub 1? A sub 1 needs to be S plus 1 times f of s. But that just cancels that first s plus 1 in the denominator, and I evaluate it at what value of s? -1. So now I have 2s squared plus s plus 4. That was my numerator. Now I have s plus 2 squared plus 3 squared. That's capital F of s times s plus 1, and I evaluate that at -1. So this is now 2 times -1 squared plus -1 plus 4 all over -1 plus 2 squared plus 3 squared. Upstairs I have 6 minus 1, or 5. Downstairs I have 1 squared plus 9. So A1 is 1/2. Is that okay? I now know what my e to the minus t term has as for its coefficient in the time domain. What about a sub 2? I multiply capital F of s by this s plus 2 minus J3 factor. And that leaves me then in the denominator with s plus 1 and s plus 2 minus J3. Nope, plus J3, right? Because I canceled the s plus 2 minus J3 factor. I'm multiplying the sides by that factor. And what do I have upstairs? I have exactly the same numerator expression that I had before. 2s squared plus s plus 4. And I evaluate this where the denominator associated with a sub 2 vanishes, and that was at its pole location of -2 plus J3. Questions on that? This is critical. You need to make sure that you keep the right root and you don't cancel the wrong factor in the denominator. That s plus 2 quantity squared plus 3 squared factors into this piece times an s plus 2 minus J3. And you need to convince yourself of that tonight when you go home. Now we simply plug in that value for the complex. And I work this on some YouTube videos so that you can let your calculator do all of this, right? But now you plug in 2 times s squared minus 2 plus J3 squared. And this is why Dr. Marsland was teaching you all this complex algebra, right? Plus s, which is -2 plus J3, plus 4 all over -2 plus J3 j3 plus 1 times minus 2 plus j3 plus 2 plus j3. If you get something 0 in the denominator at this point, you've made a mistake. Because you shouldn't have things blowing up on you. Now you do the algebra. And hopefully after you've done the algebra, you end up with minus 8 minus j21 for the numerator, minus 18 minus j6. And I like to just sketch these in the complex plane so that I know where my vectors are. I have two negative real parts, and I am going down into the third quadrant with my imaginary piece of those two. And I'm taking the ratio. So if I'm taking the quotient of complex numbers, I probably want them in polar form. This one now ends up being 22.47 as a magnitude. And what's the angle? It's going to be an angle that puts me in the third quadrant, which better be between minus 180 and let's say minus 90 in terms of its range. And it's minus 110.8 degrees. The denominator is going to be a little bit bigger than 18. It's actually 18.97 at an angle of minus 161.6 degrees. Now with quotients, I just take the quotient of the magnitudes and subtract the angles. And I end up with, for my a sub 2 coefficient, 1.184 at an angle of positive 50.8 degrees. Now I solve for a sub 3. That's 2s squared plus s plus 4, s plus 1, s plus 2 minus j3, all evaluated at s equal minus 2 minus j3. But lo and behold, it's just the complex conjugate of a sub 2, so you really don't have to do anything except change the sign of your angle. So a sub 3 ends up being what? Has the same magnitude, doesn't it? If I need the conjugate of a sub 2, I simply keep the magnitude and change the sign. And now my expression for f of s, my partial fraction expansion, is a sub 1 over s plus 1 plus a sub 2, which was 1.184 at an angle of 50.8 degrees, all over s plus 2 minus j3 plus 1.184 at an angle of minus 50.8 degrees, all over s plus 2 plus j3, which we can immediately take into the time domain. We have 1/2 e to the minus t plus 1.184 at an angle of 50.8 degrees e to the minus 2 plus j3 t. That's just an exponential with complex numbers, plus 1.184 at an angle of minus 50.8 degrees e to the minus 2 plus, minus j3 t. And we'll have to pick up at that point, or maybe I'll let you, that should combine to give you real numbers, decaying exponentials with cosines and sines. In this case, cosines at a certain angle. And we'll pick up at that point Tuesday.